Well, thank you very much for the invitation. So this talk will be a bit off topic. I consider myself mostly as an analyst working in non-symmetric spaces. But the good news is that I'm aware that it's quite different from the rest of the conference, so I try to be very basic, and I hope that you'll still get more or less what I do. So I was told that some people are interested in quasiconformal mappings, and this is sort of my view on quasiconformal mappings. Okay, the problem around which this talk evolves around is the uniformization problem. And so it can be phrased as follows. We have a metric space X, which is homeomorphic to some model space M. And we want to find conditions on X such that there exists a sort of parametrization that behaves nicely in a geometric and analytic point of view. So we start with dimension 1. There, it's a fairly easy, satisfactory answer is if one has the condition of a curve being locally rectifiable, so of locally finite length. Then we can always parameterize it by arc length. And this arc length parameterization somehow is a one-Lipschitz function, and therefore it's also differentiable almost everywhere and whatever. So it's a nice, from like a geometric and analytic point of view, it's a very good parameterization. So we can, of course, ask ourselves this question, what happens if we go to dimension 2? And there, some of you might also know the answer, at least in the smooth case. In the smooth case, we have the classical uniformization theorem, which tells us that if we have given a simply connected Riemann surface, then we know there exists a conformal map from one of these three spaces, so either the unit disk, the complex plane, or the Riemann sphere, to your space. And this also gives somehow a characterizations of simply connected Riemann surfaces, and that's why it's, in some sense, uniformization. Yes. So conformal maps are quite nice. So they're diffeomorphism, which are locally angle preserving, and they're also locally bi-Lipschitz because of that. So sort of distances don't enlarge too much or decrease too much, and they send very small balls to very small balls. So that's because they're somehow angle preserving. Now, what we're talking about in this talk is how can one think of generalizations of this theorem when going to non-smooth spaces. And the objects we consider are called metric surfaces. So it's just a metric space which is homeomorphic to a two-dimensional, or which is a two-dimensional manifold, but a smooth two-dimensional manifold. And maybe you wonder right now, well, why do we care about these objects? And they appear very naturally. So for example, what one could have is it's, in some sense, a deformation of a smooth object. I have a little picture here, and I also have the folded one here. So that's called a magic ball in origami language. And you can think of it, so it's made out of a cylinder that is just folded, and then you get this little thing here. And of course, this is still a topological, or annulus, I guess, a topological annulus. But if you would continue to folding around the holes here, or like the poles, infinitely often, then the hole would close. And what you get is somehow you have a topological sphere which very much behaves like an annulus from a metric point of view. Or maybe another illustration, you take a plane and you sort of quotient out a disk. So it's that, you can imagine. So the disk will become 1 point, and that's again a metric space. You can define a metric on it, the quotient metric. And what happens is everywhere except in this 1 point, it still looks like the plane, but around this point, there are a lot of wrinkles. So in some sense, this point behaves like a bigger set. So these are examples of metric surfaces. Other examples you can get by taking a sequence of Riemannian surfaces, and then in the limit, a lot of singularities might appear. Okay? Or the third group of examples I want to mention are boundaries of Gromov hyperbolic groups. So in geometric group theory, somehow these objects also appear in case these boundaries are homomorphic to something two-dimensional. So what is our goal? Our goal is to find conditions on such a metric surface X, such that we find a parametrization satisfying certain properties. And of course, the first question that pops up in your head might be, well, what kind of parametrization can we expect? Yes?
Assume that these metric spaces are geodesic, which means that the distance is realized by the arc length of a...
Yes, sometimes we do, yes. I guess, yeah, not always, sometimes, but in general, no. Okay, so what kind of parametrization can we expect? The first guess would be maybe we can find an Lipschitz parametrization, okay? Because we had that sort of the arc length parametrization of the curve was Lipschitz, 1 Lipschitz even. And we make an observation, so if a map parametrization is Lipschitz, then we somehow get an upper bound on the length of curves just by knowing the length of the original curve. So of the image compared to the original curve. And this means that every pair of points can be joined by a curve of finite length if we have a Lipschitz parametrization. Now, I've drawn a little picture here. It's not as nice as I expected, but what you can think of it is you take a curve which sort of oscillates around 0, and you scale it a little bit such that this surface here, so the surface of revolution, satisfies these properties. So it possesses finite Hausdorff-2 measure. If you don't know what Hausdorff-2 measure is, for open subsets of Euclidean space, it's just the Lebesgue measure. Okay, it's the same. And it somehow gives us a notion of area on these surfaces. And then, well, this surface of revolution that I just described is smooth except in 1 point, which is the origin. And we also observed that every curve passing through this 1 point has to go through the whole oscillation somehow, and therefore it's a curve of infinite length.
What is the distance of the point 0?
It's the length metric on the surface. Yes. So, in fact, around this point, not even locally, we can parameterize it with a Lipschitz function. So we have to be a bit more creative in looking for parameterizations of such a surface. And in particular, we can also not expect conformal parameterizations, of course, because everything is somehow non-smooth. So we try to look for somehow generalizations of conformal maps that we want to parameterize these surfaces with. And so I said before that a conformal map maps a small ball to a small ball. And here, the first class of mapping that we're actually going to look at are quasisymmetries. And that's a very hand-wavy definition, because I don't want to get too much into detail. But what it does, it maps sort of balls to something that behaves like a ball. And what I mean is that you can inscribe a ball of radius small r and circumscribe a ball of radius big R, and their ratio of the radii big R divided by small r is uniformly bounded. The next class of mappings we're going to look at are quasiconformal mappings, and you can think of them doing the same thing. It's also homomorphism, but it only does it for very, very small balls, like the conformal mappings. And finally, the last class of mappings we're looking at are weakly quasiconformal mappings, and there they have the same distortion property as quasiconformal mappings in some sense, but these are not homeomorphisms anymore. So these are almost homeomorphisms in the sense that they might collapse. Okay, this is also somehow an outline of the rest of this talk. I will define it later on. So these are more hand-wavy definitions of what we're going to look at. So quasisymmetric uniformization, the first sort of breakthrough result or the most well-known result in this whole non-smooth uniformization business is a result due to Bonk and Kleiner. And they say that if you have a metric surface, which is homeomorphic to the sphere, or it's a metric sphere, which is alphas 2 regular, I'm defining it in a second, then we find a quasi-symmetric parametrization if and only if this space is something called linearly locally contractible. The alphas 2 regularity means that the Hausdorff measure of a ball behaves like R squared. So somehow the area of the surface is a little bit like R2 in some sense. So that's the first condition, and linear local contractibility is defined by saying that small enough balls are contractible in somehow a scaled ball around the same point with a uniform constant. So I have a ball of radius small r around x, and I can contract it in the ball of radius lambda times r around x. And maybe to see that second condition, it prevents surfaces from having cusps, for example, infinite cusps, because, well, we can choose a radius r as small as we want, and if we go high up in the cusp, we pick a point, and then the sort of metric ball around this point is actually a topological annulus. So by metric ball, I mean all points with distance less than r. So it will go all around the cusp, and you can't contract one topological annulus inside another one. So this condition prevents these things, also like thin bottlenecks, something very similar, and also dense wrinkles. So in some sense, it's also a connectivity condition. Okay, so something I get often asked is, why do you only work in dimension 2 and not higher dimension or infinite dimensions? And it just gets much harder as you go on. And even this theorem here, it does not generalize to dimension 3 or anything above. Good. The second thing is, it's a very, very nice result, but somehow this alphas 2 regularity one would like to get rid of it. And there are two reasons. The first reason is that it's not a quasi-symmetric invariant. So I have this mapping here, the identity mapping from the sphere to, again, the sphere, but with another metric. So we scale the metric to the power of alpha for some alpha between 0 and 1. This is a well-defined metric space. And this space here is alphas 2 divided by alpha regular and not alphas 2 regular. So somehow the map is a very nice quasi-symmetry, but yeah, the alphas 2 regularity fails. And the second reason is that somehow if one would have the same statement as above, but without this alphas 2 regularity, then one would solve a conjecture in geometric group theory known as Cannon's conjecture. So this conjecture tells us that if we have a Gromov hyperbolic group whose boundary at infinity is homomorphic to the sphere, then this is a Kleinian group. meaning it admits a very nice action on hyperbolic free space. And if you're interested in why or how these two statements are related, you can ask a question at the end. Okay, so that's quasisymmetric uniformization, and I'm just saying that to sort of emphasize why this story is not finished here, and why we're looking for further generalizations of this theorem of Bonk-Kleiner. And the next generalization is, instead of talking about quasisymmetries, one talks about quasiconformal mappings, and then one can show that this alpha-2 regularity assumption can be removed. And I said before what, in a very hand-wavy way, what a quasiconformal map is. It has this distortion of shapes of sets on infinitesimal scales. And somehow what we would like to think this distortion about is, instead of shapes of sets, we look at families of curves and somehow define a measure on curves or all curves on a space, and we want to know how a map sort of changes this measure in some sense. So that's very, very broad. And of course, how can we measure the some sense largeness of families of curves? And this is known as modulus of curve families. So that's an outer measure of curves on a metric space. And we can define it as follows. So first, we sort of put weights on our space. So that's the role of this letter rho. And so we have this weight on our space such that all the curves in the family, they have a length at least 1. I'm going to make an example in a second. And then we sort of take the infimum of the L2 norm squared over all these weights that satisfy this condition. And the example that I will do is also drawn over there. So if we look at the square, or rather a rectangle, we have this rectangle of side length A and B, and we look at the family of curves connecting the horizontal sides. So that's gamma. What we can observe is that if we pick an element, little gamma in gamma, then the length of little gamma is bigger than B. So if we pick rho as being 1 over B, this condition here is satisfied for all curves in this family. And now we're interested in the modulus of this curve family of all curves connecting sort of these two sides. Now that's just, because it's an infimum, it's less than integrating this rho squared over, let's call this Q over Q. And so that's just the area of Q divided by B squared, okay? Which is A times B divided by B squared. So it's A divided by B. But that's an example of sort of what this model somehow wants to measure. Okay. And similarly, we can do the same or a similar, I'm just saying it's a less than equal here, that by taking sort of the straight lines and doing a Fubini type of argument, you can show that it has to be equal, actually. And similar, we can also compute the modulus of the curve family connecting a ball of radius small r to the outside of a ball of radius big R. And that's just this 2 pi times the logarithm of big R divided by small r to the power of -1.
Q.
This is in R2, so it's just.
And what is DH2 in formula?
That's the house of measure. So that's, yes. So H2 is always refers to the house. Are there other questions? So what I haven't said so far is that this modulus is a conformal invariant. So if I would have a map maybe from R2 to R2, which is conformal, then, and I take a curve family and map it over, it has the same modulus. So it's very natural to define a quasi-conformal map by having a modulus being invariant up to a multiplicative constant. Okay? And this is called geometric quasiconformality, but there are other notions of quasiconformality, which in general in this metric space setting are not equivalent, but in Euclidean setting, they're all equivalent. So if you prefer to think about any other notion of quasiconformality in R2, you can. So one thing I want to observe is the following. So here, we've said that the modulus of the curve family connecting sort of horizontal sides is A over B. If we multiply it by sort of the dual modulus, so the modulus of the curve family connecting the vertical sides, then we just get 1. Okay? So it's A over B times B over A, which is just 1. So that's one observation. This holds for every rectangle or in the plane. And the other observation is if we have a point and we sort of look at this curve family of these two annuli, or of the annuli, so connecting the two sides of an annuli, and we let the small radius go to 0, then this modulus goes to 0 too. So somehow it tells us there are not many curves going out from one point. Okay, so these are two conditions. And now if we have a geometrically quasi-conformal map, then of course we get to very similar conditions on our metric surface. So once we assume the existence of a parametrization by a geometrically quasi-conformal map, we get that these two conditions hold. And well, for example, R2 satisfies these, that's what I've shown before, but also all our alphas 2 regular metric surfaces satisfy these two properties. And it's a theorem of Riemann, who then said that, well, given the metric surface homomorphic to R2, which has locally finite house of 2 measure, meaning that, well, locally we have finite area, so it's not a fractal surface in some sense, but it's something that behaves nice, then we always find a geometrically quasi-conformal map from a domain in R2 onto our surface, so a parametrization, if and only if the surface satisfies these two properties. So one direction we did, it's easy. So once we have the existence of a quasi-conformal parametrization, we automatically get these two conditions. But he showed that indeed these conditions are sufficient for the existence of such a parametrization. And he calls such a surface reciprocal. And well, the word comes because in Euclidean R2, sort of the product of these two moduli is just 1. So one is the reciprocal of the other.
Gamma star for a general?
So gamma is connecting sort of horizontal sides, and gamma star is connecting vertical sides.
Also the Q?
These are somehow curve families that are somehow dual to each other.
What is horizontal and vertical?
Yeah, well, you in a metric space, you take a Jordan domain and you fix some points, and you just say the curve family joining opposite sides, the two different curve families. You can identify every Jordan domain as being a somehow topological quadrilateral. Other questions? So maybe a few comments on this theorem. So I said before that alpha's two regular spaces are reciprocal. So by this theorem, we get the existence of a quasiconformal map. And if we also assume this linear local contractibility condition, then quasiconformality upgrades to quasisymmetry. This is not for free because I said before quasisymmetry is a condition that holds for all balls, and somehow quasiconformality is this condition holding only for the infinitesimal balls. So we need to have additional assumptions such that we get that quasiconformality upgrades to quasisymmetry. And yes, we therefore recover the theorem of Bonk and Kleiner. So that's the first comment. And then we had before these two conditions, and it actually holds that for every such metric surface, the lower bound in one always holds with a certain constant here. And also the upper bound sort of implies the second condition, but not the other way around. So there is an example of a metric surface that is not reciprocal, but satisfies condition 2. So in summary, we could just define a metric surface to be reciprocal if we have a constant such that for every quadrilateral, we get that the product of these dual curve families, of the moduli of these dual curve families, is bounded from above. So there's somehow two problems. So in general, it's very hard to verify this condition. So there are a few conditions known that imply reciprocality, but if I give you a metric surface, how do you verify that? It's very complicated somehow. And the second problem is that there exist plenty of metric surfaces that are not reciprocal. So one is interested in further generalizations. And I want to make an example of a metric surface that is not reciprocal. And it's essentially this one here that we've seen. So by collapsing a disk. So, and here we start with the unit disk, and we collapse a small ball T in our space, and we look at the quotient space. And then we, of course, have the natural protection. And this is a local isometry everywhere except in this small ball that we collapse. And it sends this ball T to just one point. So now what we're going to consider is sort of the modulus of the curve family that I drew here of radius small r around x0, connecting this ball to the outside of the bigger ball, around this one point that is the image of the collapsed disk. And what we compute is the following. We can observe that because it's a local isometry outside of T, the modulus is the same as the Euclidean modulus of sort of the curve family connecting the ball of radius r plus epsilon around 0 with the outside of the ball of big R plus epsilon around 0. And we have a formula for that. And we see that if we let little r go to 0 in that formula, it will always be strictly bigger than 0. And the moral of the story is that sort of if we look at all the curves going out from this one point, there are way too many curves. Okay? Because of all these dense wrinkles, in some sense, we have a lot of curves going out from that point. And so this is condition 2. Condition 2 should be 0. And we had before that condition 1 implies condition 2. So in particular, condition 1 is not satisfied. And therefore, this is not a reciprocal metric surface, even though it's a very simple and canonical example. You just collapse the set. So can we somehow construct a good parametrization of a general metric surface? And this is why we look for the third class of mappings that I mentioned, and these are called weakly quasiconformal mappings. So we go to the compact case now because the definition of weak quasiconformality is a little bit easier there. Then the map is just a uniform limit of homeomorphisms. So that's what I meant with an almost homeomorphism before. And we have that one of these modulus bounds holds for every family of curves in our surface M. The other one does not hold because we can collapse things. Okay, and it was a question by Riemann and Wenger whether one can always find such a parametrization, and the answer is yes. In case we're locally geodesic, meaning that at every point we find a neighborhood such that every pair of points in this neighborhood can be connected by a curve whose length realizes their distance. So that's to your question. Here we assume that it's locally geodesic, and that's work of my advisor, Stefan Wenger, and myself. And at the very same time, without us knowing, and by applying a very different strategy, Dallenbeckers and Romney were working on it. And somehow, with their proof strategy, they were able to drop this assumption of being locally geodesic. So they somehow completed the story of uniformization of metric surfaces. Good. And also just to mention, in case X is reciprocal, we can again upgrade our map to being a quasiconformal homeomorphism and thus recover the previous theorems. So I will state the theorem in case of the disk. It's like that. So we have a locally geodesic metric surface, which is homeomorphic to the closed unit disk. And if we assume that the Hausdorff measure is finite and the boundary length is finite, then we find such a nice parametrization. And so the strategy of proof, in some sense, in our setting, is to use the solution of Plateau's problem. So Plateau's problem is as follows. We have given a rectifiable Jordan curve in some space, and we want to find sort of the surface that spans this curve, which has minimal area among all such surfaces. And it is often much more convenient to work with energy instead of area when you minimize these. So we have some class of mappings from the disk into our surface, which somehow span the surface. So that's the assumptions are that the mappings have a certain regularity, they're Sobolev. This we do just to define a notion of energy. And their trace is an almost parametrization of the boundary, so they somehow span the surface, or span gamma. And I'll skip the definition of metric space values Sobolev maps just because it's a bit technical. But what one wants to show is that sort of this space, lambda of x, is non-empty. And I'm just saying this is highly non-trivial because X might be very ugly. That's what I'm trying to describe in these words. Don't worry if you don't understand it. So it might contain a very, very ugly set. And therefore, there exists only very few Lipschitz maps from open subsets of R2 to our space. And somehow Sobolev maps are somehow generalizations of Lipschitz maps, if you want to say so. So it's fairly non-trivial that such a Sobolev map even exists. So this is a large part of our work is sort of devoted that actually we can find a Sobolev map from the disk to such a general metric surface. And in the next step, what one does is one tries to show the existence of a energy minimizer in this set lambda of x, and that's a direct variational method. So we take an energy minimizing sequence, and we want that limit somehow or that it converges, or a subsequent converges, and the limit is again in the set. So that's a quite standard method. And then, once we have an energy minimizer, we want to show that it has a continuous representative. And this is because it's energy minimizing, it has to have some certain further regularity properties. It's crucial that it minimizes the energy. And then we also get some more, in some sense, topological properties, that it has to be a uniform limit of homeomorphisms. And in the last step, we get this distortion property that we want. And there you can think of it, well, if we have a map sending a small ball to our metric surface, which is energy minimizing, if it would distort the ball very much, it would need a lot of energy. Okay? Or if it would collapse a lot of things, you would also need a lot of energy. So because it's energy minimizing, it has to send balls to something that looks like a ball, more or less. So that's sort of the way I try to think about these mappings. Now just one last application of, well, you might think now, why is this useful, knowing that the existence of these mappings, these nice parametrizations? And the application is concerning this question. So we have a map, which is one Lipschitz, so it only makes distances smaller, and it's surjective, and it is a map between metric spaces that have the same volume in some sense. So for example, metric surfaces that have the same Hausdorff-2 measure. And the question is, well, somehow the volume stays the same, but the map is only allowed to decrease distances. So does every distance have to stay the same? So that's the definition of an isometry, is when every distance has to stay. And somehow, because they have the same volume, one expects that it could hold in certain settings. And it's in some sense a folklore theorem that the answer to the question is yes, in case of X and Y being closed Riemannian N-manifolds. And I say folklore because you find proofs of the theorem, but it's not really attributed to these people. And what Bekos and I were able to show is that actually, if you go to dimension 2, you don't need to assume anything on X except it being a metric surface, and you get the same statement. And this very much depends sort of on having a nice parametrization, because when one wants to sort of work with these things, one needs to differentiate things, which is not so easy in metric spaces. But if you have a nice parametrization, you can then differentiate sort of your parametrization and the composition, and you get some additional properties of your mapping. Okay, I think this is all I wanted to say.